Okay, so we're going to go through our groups here a little bit at a time. But group 1, the alkali metals, does not include hydrogen. So it includes elements lithium, sodium, potassium, rubidium, cesium, francium. Okay, so you don't have to write down the individual elements. As long as you can locate where group 1 is, you should know those are your alkali metals. Okay, with the exception of hydrogen. Okay. Hydrogen only sits in group 1 because it has similar characteristics to the group 1 metals. And we'll talk about that here in a second. Okay, they all have this kind of silvery, shimmery appearance. They're not super, super shiny like some of the examples we looked at last class in terms of shine on metals, but they do have sort of a silvery kind of luster to them. The group 1 metals are really soft. So we talked about some metals can be cut with a knife, right, or a scalpel type instrument. These would be examples of that. So especially, well, all of these group 1 metals, very, very soft. Okay, so farther left on the periodic table, we'll get a really soft metal. Okay, these elements are not found alone in nature. So you won't walk down, like the street or wherever you're going, and find a chunk of sodium metal sitting there. Okay. Okay, a valence electron is an outer shell electron. So I'm going to put that up here. Okay. They have one valence electron. And what a valence electron is, valence electrons are electrons in the outermost shell of an atom. Okay, is that ringing bells a little bit more now? The outermost shell of an atom contains valence electrons. And so, does anyone remember how many electrons an atom needs to feel complete? To be complete, how many electrons do we need? It's between 7 and 9. 8. Okay, we need 8 electrons. Okay, an atom needs 8 electrons in its outer shell to be what we consider complete, to have a full octet. Right, that's called the octet rule. So I'm just introducing this to you now so you have a little bit better understanding. But the octet rule means an atom would like 8 electrons to feel complete. Okay. And so the group 1 metals only have one valence electron. So is it easiest for them to find 7 electrons or to give away their one? Their one in the outer shell. To give away their one, right? So let's see if I have an example here. Let's say I have sodium. Oops, sorry. Let's say I have sodium. I'm just going to draw kind of a shell form, right? Here's sodium. All of these are full of 8 electrons, even the one I'm not drawing underneath. Sodium's in the 3rd period, which means it has 3 shells of electrons, and it's got 1 in its outermost shell. Okay? So if it can get rid of that outermost shell electron and give it to someone else, it removes that outer shell, and then it now has 8 electrons in its outer shell, which makes it happy. Right? It's complete. It's got 8 electrons. So having that 1 electron in its outer shell means it will give away that electron to anything and everything to chemically bond with another atom. Right? It wants to give that electron away. So it's super, super reactive. Okay? It will bond with anything and everything. Okay? So that's why we don't see calcium metal just sitting around, right? Or sodium metal or potassium metal just sitting around. It's so reactive it will react with anything. It will bond with anything. We'll see it in multiple forms. So these metals that we ingest, we are ingesting as a chemical compound, right? It's potassium bonded with something else. And then our body is able to extract that potassium and absorb it the way our body needs. So we're not ingesting potassium metal. We're ingesting potassium in the form of a chemical compound as it's bonded with something else. And then our body does the rest of the work to extract that potassium. Okay, so if we have time later, I'll look up exactly what chemical compound is in bananas that contains potassium, because I've never looked that up before, but we can find out in what way our body is ingesting that and extracting that potassium. Okay, but does that make sense? 1 valence electron means super reactive, because it's much easier to give away 1 than to bring in 7. Right, would you agree with that? Okay. So we're going to watch a short little video here on the group 1 metals, because they are super, super reactive, especially with water. Okay? So I'm going to watch just a quick video. Okay, moving to the right, group 2 is the alkaline earth metals. What elements are involved in group 2? Take a look at your periodic table. What elements are included in group 2? Anybody know? Find group 2. What elements are they? Just say them. Beryllium, magnesium, calcium, strontium, barium, and radium. Okay, so those are the group 2 elements. You don't have to write these elements down if you know where group 2 is. Okay, if you can locate group 2, there's no reason to try to memorize those. You will always get a periodic table. Okay, so you can find group 2. All right, as we move toward the middle of the periodic table, you'll see that metals start taking on what we would consider to be more metallic type properties, right? They become tougher, denser, harder type materials. So they're not, the group 2 metals still aren't, like iron type toughness, but they're getting there. They are more tough than the group 1 metals. Okay? They have what we would consider higher melting points, and a melting point is exactly how it sounds. It's the temperature at which an object melts, so it goes from solid to liquid. Okay? Higher melting points means we have to put in more energy for those bonds to break, which means those metal atoms are bonded together more strongly than the group 1 metals. Okay, so higher melting points than group 1. They are a little bit less reactive than group 1 as well. Okay, a little bit less reactive. Can we start to think about why that might be? Why might they be less reactive, knowing what we know about valence electrons? Yeah, and what do you think? They still have, they're harder, a little bit harder to bond with. Okay, what do we know about valence electrons for group 2? What was our guess? How many? 2, right? So they have to get rid of 2 electrons, not just 1. So they're still extremely reactive, but they are less reactive than group 1. Okay? They're still too reactive to be found in nature. So like we said, we're not going to walk down the street and see a hunk of calcium metal sitting there. Okay, they're still too reactive to be found in nature, but they're very reactive because they have 2 valence electrons to get rid of. Okay, so it's tougher to get rid of 2 than 1, but it's still easier to get rid of 2 than to find 6 more. Okay, to fulfill their octet. Okay, so that's what calcium metal would look like, right, or does look like in a lab setting. You can see based on kind of this kind of pebble-like texture of calcium, it's a little bit more brittle, right? It's not the soft chunk like we would see with sodium or potassium or lithium, things like that. So it's a little bit more brittle, but that's what calcium metal looks like. Okay, so still very reactive. They still want to bond with things much more so than the middle group of elements, but not as reactive as group 1. Okay, so group 2 in general, pretty reactive. So group 1 has 1 valence electron, group 2 has 2 valence electrons. Okay, now we're going to look at what we call the transition elements or the transition metals. These are groups 3 through 12, so this chunk right in the middle here. Okay, I call those the transition metals, okay, because they're all metals. So sometimes your book calls them the transition elements. It doesn't make a huge difference. But you'll hear me call them the transition metals. Okay, they have what we would consider very typical metallic properties. Okay, and if you know the metallic properties, we wrote them down last class, you don't have to write them down again. So they're good conductors, they're shiny, they're not very reactive, and many of them exist as free elements. And what that means, when I say free elements, that means it doesn't have to be bonded to anything. And that means they are okay hanging out by themselves. there's the rest of our metallic properties we talked about. Except the problem with the transition metals is that they don't follow the trends with valence electrons. Okay, so that means group 3 doesn't necessarily have 3 valence electrons. Group 4 doesn't necessarily have 4. Okay, they don't follow the trends there. So when we talk about trends with valence electrons, we'll go group 1, group 2, and then we skip all those guys in the middle. We pick that trend to back up in 13. Okay, and we'll talk about that a little bit. But when we pick that trend back up, group 13 has 3 valence electrons. Group 14 has 4, so you kind of drop that 10 off of there. But these guys don't follow that trend. So I'll give you, I will give you something that tells you number of valence electrons to help with the charges when it comes time for that. But you just need to know that those middle ones don't quite follow that trend. Okay, any questions? Okay. So now we're going to skip over to group 16 to a group called the chalcogens. The chalcogens. So that's how you pronounce that word, chalcogens. And this is the group that contains oxygen. You'll rarely hear me say the word family in terms of a group, okay, but sometimes your textbook says that, and so sometimes I'll put it up here, but the chalcogen group is your group that contains oxygen. Okay, these are fairly reactive elements. Based on what we know about valence electrons, how many valence electrons would you guess the group 16 elements have? Yeah. 6, right? 6. Good. We dropped that 10 from the transition elements. There's 10 groups of transition elements. Okay, so sometimes people even number their groups 1, 2, and then they skip over here to 3, 4, 5, 6, 7, 8 okay, to help follow that trend. But we'll name them 1 through 18. Okay. In group 16, we have kind of a wide range of properties. So if you look at your periodic table, you'll see that you have some nonmetals, you have some metalloids, and you have some metals within that chalcogen family. Okay, if you shaded your periodic table, you might see that transition of color. Right? We have some nonmetals, some metals, and some metalloids. Okay? Oxygen is the only one in the chalcogen group that has a gas, or that is a gas at room temp. Everything else is a solid at room temp. They tend to form a compound, or they tend to bond with elements from the metals side. Okay, we're going to look a lot more at chemical bonding and chemical compounds later this semester, but these guys tend to form compounds with a metal, and those compounds then tend to be not soluble in water. Do we know what the word soluble means? Soluble means able to dissolve. So if they're non-soluble, that means they won't dissolve in water. Okay. So we talked about the fact they can be metals, metalloids, or metals. You don't have to necessarily write that part down, but as you look through that group, I want you to be able to see that change. Okay, some of them are metals, some of them are metalloids, and some of them are non-metals. Okay, the very last one in group 16 is called livermorium, and that's a man-made element. Okay, man-made element. Do we know how many man-made elements there are? That's a number that you should think about, maybe remember. 35. Okay, 35 man-made elements. Okay, so 35 man-made elements. That's a number that we should know. Okay, so maybe highlight that or put a star by it or whatever you want to do. You'll need to find that again in your notes. Okay, so that was group 17. Any questions with that? Okay. The noble gases are group 18. Okay. What state do you think they're all in? Gas, right? Otherwise it'd be kind of a silly name. Okay, they are the noble gases. They are generally extremely unreactive. Can anyone think about why that might be the case? Yeah, Kate. Good. They have 8 valence electrons, and that's exactly what they need, so they don't need to bond with anything else. Okay? All of them are gases at room temp. They're unreactive. They have full outer shells, which means they have 8 valence electrons. So if you want to write that separately or, right beside there, that means they have 8 valence electrons. Okay, and when I write an E with a minus sign, that means I'm writing electrons. So this abbreviation right here for me means valence electrons. Okay, whenever you see this E with a minus, crazy E, an E with a minus, that is valence electrons. Okay. These are all used in what we consider to be neon lights, right? We call them neon lights because neon is used, but all of those noble gases give off different colors. So depending on the color you want to display with your neon gas, you put a mixture of these neon gases in there. Okay, so all of them give off different shades of that neon kind of color. Okay, so it's not necessarily just neon that goes into a neon light. They give up all different colors. And then you can mix them depending on what color you would like. All right, the last 2 parts of the periodic table we're going to talk about are called the lanthanides and the actinides. The lanthanides and the actinides are the 2 bottom rows that are pulled out and sit at the bottom of your periodic table. So the lanthanides are atomic numbers 58 through 71. They are shiny metals, and they behave similarly to group 2. Okay, so similarly to the alkaline earth metals. And you see that this called a group, but not really a group because it's not vertical. The lanthanides sit right here. Okay, and some periodic tables have a little line drawn up to here to show this is where they fit in the periodic table. But where you see on your periodic table, it actually has lanthanum and actinium in here. Okay, but like on my periodic table, it takes them out and sits them below. It doesn't matter which way your periodic table shows it, but that's where they fit. It's right in here. Okay, and I'll show you what that would look like if they sat where they were supposed to in the periodic table. The actinides sit directly below them. These are all usually radioactive elements. So these are the number 90 through 103. So actinium is actually number 89, and then the series continues after that from 90 to 103. Same with lanthanum, it's actually 57, so the 58 is following lanthanum. Okay. So in some periodic tables, lanthanum and actinium will sit in the actual periodic table. Sometimes they're pulled out below. Okay. The actinides are radioactive. Some are found on Earth, but most are man-made. Okay. And the way you can tell a man-made element is if you look at that periodic table up there, the white elements, or just the outlined elements, those are your man-made elements. Okay. And there's even those empty boxes are filled in by this point. But you'll notice your man-made elements have kind of almost recognizable names, right? If you look at 98, californium, einsteinium. Okay, those are elements that man made, and then once you make an element, you get to name it whatever you want. Okay. So you'll see a little bit more familiarized names. Otherwise, the names come from kind of a Latin base, and so that's why things like silver and gold, which are silver's 47, so kind of right here in the middle, gold's right underneath it. That's why silver doesn't have just an Si for its atomic symbol, and gold doesn't have Go, right? It's based on a kind of a Latin name, Latin original name. Okay. So if the lanthanides and the actinides were to sit in the periodic table where they go, that's what it would look like. It's a little bit awkward. They don't give them group numbers. It skips over here to group 3 because they don't really follow trends like everything else. So they pull them out and put them below the periodic table to kind of save space and make it a little bit more compact. So that's what it would look like if lanthanum and actinium fit in the periodic table exactly as they should. They pull them out for space reasons. Okay, any questions? Okay.